Welcome to my video about tangents. Tangents. A line tangent to a circle is a line that intersects a circle in exactly one point. That point is called the point of tangency. A line is tangent to a circle if and only if it is perpendicular to a radius at the point of tangency. Okay, if our line RS in the circle above is tangent, then point R is the point of tangency, and the measure of angle PRS is 90 degrees. Okay, so here is my tangent line, and its point of tangency to the circle where it touches the circle in exactly one point is point R. Okay, and then my radius, PR, is perpendicular at that point, and so angle PRS is 90 degrees. All right, so let's look at some examples and kind of go through this together. All right, do the figures below contain tangent segments? So the only way that this is tangent is if it's perpendicular to this. And so it looks like we have a triangle here, and we could check to see if a squared plus b squared equals c squared. If it is, then it is a tangent. It does contain a tangent segment, which would be the segment right here. All right, so we are checking to see if this is tangent by using the Pythagorean theorem. We have a squared plus b squared. Whoops. We have a squared plus b squared, and we want it to equal c squared. Okay, so 13 squared plus 84 squared and 85 squared. So we're going to compare those, and if it's equal, then we will have a right triangle. All right, so 13 squared is 169, 84 squared is 7,056, and 85 squared is 7,225. Okay, so let's add these together, and it does equal 7,225. And therefore, a squared plus b squared does equal c squared, and we have a right triangle. So yes, it does have a tangent. All right, let's look at this one. We want to know if this is a right angle or not. If it is, then we have a tangent. All right, so we know that if this is the right angle, then this would be our C, okay? And we want to see if a squared plus b squared is equal to c squared. Okay, so we have 24 squared plus 9 squared, and how does that compare to 24 squared? Well, first of all, we can tell right now that isn't the hypotenuse always the longest side of the triangle? So it's no way that 24 would be the hypotenuse. But we'll go ahead and do the math anyway. We get 625 plus 81. And how does that compare to 576? Well, this is 706, so this is too small. So we have an acute triangle. So the answer is no. There is not a tangent segment. It does not contain a tangent segment. One more type of question. If AB is tangent to circle C, okay, so again, this would be the right triangle at the point of tangency, the right angle, and so 9 is our hypotenuse. So we have x squared plus 8 squared. AC is not 9, but AD is 9. but I know that this is the radius right here, and so it's going to be the same as 8. So what is 9 plus 8? That's 17. X squared plus 64 is equal to 289. Subtract 64 from both sides, we get x squared is equal to 225. And so when we take the square root of both sides, we get x is the square root of 225, which is 15. So x is 15. Another property of the tangent is if two segments from the same exterior point are tangent to a circle, then they are congruent. So if lines RS and ST are tangents, then they intersect at this point S, then we know that segment RS is congruent to segment ST. So these are congruent. All right, so let's look at this example here. And I'm going to put on here if segments appear to be tangent, they are tangent. All right, let's look at this first one. We have circle M, and we have two tangent lines. We have one here NP, there's tangent segments, and QP, and they intersect at P. That means these two segments have to be congruent. So X is 12. All right, on this one, again, we have two segments that are tangent to and they intersect at a point outside the circle. That means these two segments are equal. So X plus 3 equals 7. And then we just solve, and we get X equals 4. Let's look at circumscribed polygons. When a polygon is circumscribed about a circle, all of the sides of the polygon are tangent to the circle. So all of these sides all touch the circle at those one point of tangencies, one for each one of them. Okay, so hexagon ABCDEF is circumscribed about circle P. So inscribed is on the inside of the circle, circumscribed, so written around, is on the outside. Squared GHJK is circumscribed about circle Q. And all of these segments, all of the sides of the square, are tangent to Q. And so if we look at one of them, the square is a little bit easier to see, but we have this point, all of these points of tangency, okay? So this tangent line HJ and GH, they both intersect at that point H. So that means these two little segments have to be equal. Then we have these two segments that intersect outside the circle, and they're congruent. These are congruent, and these are congruent. And on a square, they are all congruent to each other, but not all figures have that. So like, for example, this triangle right here, triangle ABC is circumscribed about circle O. Find AD and the perimeter of segment, or of triangle ABC. So AD is this segment right here. Well, I know that all these lines are tangent to the circles because it says it's circumscribed. And so we have points of tangency. And from that point of tangency to the point outside, those tangent lines are congruent. So AD is going to equal 12. All right, so that one's 12. This one is congruent to this one here, so that's a 6. It's kind of a messy right there. Let me erase that, make this bigger. So this is a 6. And then here, this little segment is an 8, because they intersect, these two segments intersect at the C. And now we can add up all the sides. So this is 20. 12 and 6 is 18. 6 and 8 is 14. So we have 20, 18, 14 is 52. So the perimeter is 52 units. I'm going to end the video here, and we will do these mixed practice problems in class.